Hey everybody, Physics C students. I'm gonna make my second rotational kinetic energy video here. My daughter's yelling upstairs. Probably hear her. Um, uh, anyhow, the I messed up the homework assignment a little bit. I didn't mean for these 1, 2, and 3. It was the 1 and 2 in the digital version, which actually are 6 and 7 over here. 6 and 7. I am going to go through right now 4 and 5 for you. What's called the parallel axis theorem, and talk a little bit about calculating rotational kinetic energy in this video. The parallel axis theorem is useful. That's something that is often on the AP exam. Who knows with what this exam is going to look like this year, but I'll go through it here. For you. I basically have already done 1, 2, 3 for you and done this derivation here. So, read those notes, okay? And see if you can fill this in. I'm going to post solutions. What I did, the photocopied version I had given you was correct. So that those of you that didn't get the photocopied version, which I think was Saranya, maybe Leah. But anyhow, I will fix this file on my CBA as soon as possible. So let's talk about parallel axis theorem really quick here. It's pretty neat. So if you have a disk rotating, right? I talked a little bit about this in the last video, talking about the dual shock, remote, PlayStation remote. If you rotate something about a center axis, it has a certain moment of inertia, right? I equals 1/2 mr squared. Oh man, this is tough. I crushed my finger in the car door yesterday, and writing is the first time I've written since doing that, and it's not fun. All right, so anyhow, I equals 1/2 mr squared for this disk. However, if you remember, the farther away the mass gets from the rotational axis, the harder it is to turn the object, right? So think about centripetal force, so to speak, or torque wrenches, right? I got to set up my torque wrench for you. The farther you apply the force, farther the mass is away from this rotational axis, the harder it is to turn. So anyhow, here we go. How much does it change by? Well, it's really kind of a cool little result. Let's say this is our rotational axis normally, right? Our center of mass rotational moment of inertia is what this is. If we drill a hole in this disk and we make it over there now, and we shift it by some distance, let's just call that d, all right? Turns out that the new moment of inertia is whatever the moment of inertia is about the center of mass, which is this one here, plus the mass of the object times the distance you shifted the axis by squared. Really kind of a neat little result. I'm not going to go through the derivation of this, but it works, right? So it's whatever the center of mass moment inertia. So for this one, it's 1/2 capital M R squared. Let's say I shifted it by R over 2. So I split the difference here, right? Plus the mass times R over 2 squared, so that'd be R squared over 4. And then to add these two, right, I'd have to make this 2 over 4. So we'd end up with 3/4 capital M R squared for the new moment of inertia, right? Sometimes they just call it just blank I. So this is the center of mass moment inertia of the object. This is the new moment inertia. It's bigger because more of the mass is shifted away from the rotational axis. Pretty cool little thing called parallel axis theorem. Parallel axis theorem. All right, that used to show up on the AP exam quite a bit. Who knows this year? Maybe I could see them do a lab question with this, right? Like you have a disk rotating, right? And you get a I don't know, like the torque versus alpha graph, right? And you see it like this. And The theoretical, the center of mass moment inertia of it is maybe like 20 or something. However, then you see, okay, when we actually do this, torque equals I alpha, the slope of this line would be I. And you say, oh, wow, look, it's 40. So where is the rotational axis? I could see something like that because they're saying it's going to be a lab question. So maybe I'll try to make some up like that. That would actually be a really good one. Wouldn't that be wild if that ends up being one of the actual problems? Number 5 on the homework is kind of the same thing. It's just determine the moment inertia of a 1 kilogram, 0.1 meter radius solid sphere rotated by an axis parallel to and 5 centimeters from the central axis. So solid sphere, the center of mass moment inertia is 2/5 capital M R squared. All right, the mass of this thing is 1.0 kilograms. The radius is 0.10 meters. And I'm going to take this now and shift it. That's the original axis. I'm going to shift it 5 centimeters away. So now it's kind of like this weird rotating circle about the edge like in the drawing here. So 5 centimeters away, 0.05 is our D. This isn't positive or negative. It's just if I move to the left or the right, it doesn't matter. It's just the distance of your new rotational axis from your old rotational axis, the center of mass rotational axis. So your new moment of inertia is the original 2/5 capital M R squared plus my new one here, however far you shifted it by, and this is a quantitative result. It is R over 2, right, basically. So M times D, which is R over 2 in this case, squared. It's a quantitative answer. Go ahead and check out the solution to this later on. So now I got to figure out how to add these two together. Maybe it's best if I just put the numbers in. All right, 1.0 times 0.1 squared plus 1.0 times 0.05, or that's how far you shifted it by. I shouldn't have done that. I should just called it D. All right. 1.0 times 0.05. So you can plug and chug it and get an answer. All right. 2 divided by 5. Oops. 2 divided by 5 times 10 times 0.1 squared plus 1 times 0.05. That's going to give us 0.09. And what the heck are the units on these things? It's kilograms because it's mass times meters squared. So this is the moment of inertia of this object about this other axis. Parallel axis theorem, all right? Very cool. Very cool to do. Now, I was thinking about breaking this video up into 2 videos, but I'm just going to roll ahead here. So now, let's go and look at what you did for homework last night, that you probably didn't do for homework because I done messed it up. Just basic how to calculate rotational kinetic energy of something that's rotating. That's kind of the first step to being able to do these problems. Ultimately, these are just conservation of energy problems. Good old energy bar graphs could be used, right? Conservation of energy, but with the rotational kinetic energy factored in. My daughter's up there going wild. I don't know if you can hear her in this video or not. She's singing, it sounds like. A 0.15 kilogram, 0.3 meter radius bike tire rotates with a stationary center of mass at a constant angular velocity. Now, holy cow, what does that mean, a stationary center of mass? All right, it just means the bike tire is suspended. It's like you got your bike upside down and you're fixing it. My 8-year-old daughter just finally learned how to ride a 2-wheel bike, right? A little late, but, I don't blame her. I didn't start riding a bike till fairly late either, and she learned the same exact way I did. She got on a really small bike that she could easily put her feet down on and started riding that. So we're going to go maybe a little later today and try to take the training wheels off her bigger bike and see how that goes. So let's say we got the bike flips upside down. I'm changing the training wheels, right? And I give this a spin. So it's rotating, But the center of mass, which is right there, is not moving translationally. It turns out that any object's kinetic energy, it's actually a combination of the translational and the rotational kinetic energy. So the left to right, or the linear motion, the center of mass motion, I should say, the center of mass motion of the object is one component of the kinetic energy. The other component is the rotational. So if something's rotating and moving, it has two components. So its total kinetic energy is 1/2 the mass times the center of mass velocity squared plus 1/2 I omega squared. Very cool. And these two, VCM and omega, if something is rolling without slipping, meaning if we were rolling, this bike was actually turning, right, and rolling along the ground, turns out that the speed this thing moves forward with is the speed of the tangential velocity. Because think about it, if it's not slipping, imagine this was like a string and it was unwinding itself, right? It unwinds at the rate at which the outside edge of this rotates. So if the outside edge of this is rotating at 10 meters per second, well, the string's unfurling itself and the center of mass is moving forward at 10 meters per second. So if it's not slipping, we do this. V equals R omega. It's just like the torque where A equaled R alpha, and we use that equation to tie the rotational force and the linear force together and eliminate variables. We do the same thing here. Turns out that we eliminate omega. We say omega equals V over R, a bunch of stuff cancel. It's a very similar technique. This is the equation that binds V equals R omega. Anyhow, that was a little bit of a tangent, but not too bad. So stationary center of mass, that means there's no translational component. This VCM is 0. So the kinetic energy of the object is just the rotational component. So to determine the kinetic energy of the bicycle tire can be approximated as a hollow hoop, right? And it really can be, because the spokes have very little mass. The central hub is aluminum. All the mass is concentrated towards the outside. So a hollow hoop, and in fact, if you made the radius the center of the tire, that would probably be more accurate. But a hollow hoop works well for this. So the kinetic energy of the tire is 1/2 I omega squared. Write the whole thing out. One thing that happens a lot is when you plug in I, kids accidentally forget to put the coefficient on it. So in this case, the moment of inertia of a hollow hoop is mr squared, right? So we plug that in here, equals 1/2 mr squared times omega squared. We put in the numbers now. So 1/2 of the mass of this is 1.5 kilograms. The radius of the bike tire times 0.30 meters, that's squared, mr squared times omega squared, that's 30 radians per second. That's squared. So we put it all together, and I'll show you what the units end up being here in a second. So 0.5 times 1.5 times 0.3 squared times 30 squared equals 61. 61. And then what are the units? Kilograms times meter squared times radians squared per second squared. The radians squared we drop. It's an annoying thing, and it's not very satisfying for me just to tell you that, because kids never like that. But it's not really a unit. It's kind of a placeholder. So it's 61 kilograms times meter squared per second squared, which is a joule. 61 joules of rotational kinetic energy. Very cool. So that's about it for this video. Number 7. Let me set that one up for you. Actually, let me take a look at that one really quick, because this combines the translational and the rotational. This is a really important one, actually. I'm not going to skip it. So sorry, this video is going to be a little bit longer, but oh well. Number 7, a solid ball of mass 2 kilograms rolls along the ground at a constant speed of 3 meters per second. So the center of mass speed of this thing rolling across the ground is 3.0 meters per second. Determine the total kinetic energy of the ball. I don't need to say total. I could say just determine the kinetic energy of the ball. And most of you would just say, okay, that's 1/2 mv squared. Slow down. Plus 1/2 I omega squared. It's the translational kinetic energy and the rotational kinetic energy added together. So this is a little confusing at first, especially if you've never learned about this. But it needs to be accounted for. It turns out when you roll a ball down a hill, if you calculate MGH, and I know those of you that did shoot for your grade in Mr. Kalimlim's class last year, some of you learned this the hard way. It will not be moving as fast at the bottom as you calculate it ought to if you use just 1/2 mv squared. It turns out that initial gravitational energy has to go into MGH equals 1/2 mv squared plus 1/2 I omega squared. So it turns out the kinetic energy at the bottom has to take into account all the motion of the molecules. I like to think of it like this, right? Like these molecules rotating in a circle, all the molecules that make up this ball, right? They're all moving. So their kinetic energy is a combination of how fast it's going around in a circle while it's moving forward, right? So that's why you have the two components. The velocity of the mass in this object, it's got two components. It's got the rotational velocity and the translational velocity. You have to consider both of those in terms of where the energy is going. All right, so it turns out when you roll something down a hill, it doesn't move as fast at the bottom because you often aren't factoring in the rotational. So in real life, if you do the shoot for a grade lab and just try to use MGH equals 1/2 m, it will not work. It'll be moving way slower in real life. You'll greatly undershoot your target, especially with those metal ball bearings, right? They're heavy. They got a big moment of inertia. Anyhow, so this here, we're going to do more with that. So all the physics did last year, if it said a cart was rolling down a hill, it wasn't actually rolling, it was sliding. If anything's rolling, you have to factor in. So on a cart, it's kind of a fun thing they do, and we'll look at a problem like this later on. You have to factor in the rotational inertia of all four wheels. That's why Hot Wheels cars, the wheels are small and light. The cars we use in lab, the wheels are small and light, right? So not much rotational inertia. Who's there? My daughter's checking in. What are you doing? Trying to ride your bike? Okay, I was just telling them about your bike riding skills. All right, go ahead. You can open the door. Anyway, so you have multiple moments of inertia sometimes when you're dealing with wheels. So for this one, 1/2 mv squared plus 1/2 I omega squared, the total energy, we've got 0.20 kilograms. I'm not going to do the full calculation right now. I want to wind this video up. It's already gotten too long. 3.0 meters per second is the speed, plus 1/2 I omega squared, solid ball. So you got to put in 2/5 mr squared. Now, omega has to go in here, the rotation rate, right? V equals R omega. As long as it's not slipping, you say omega is V over R. That goes in here. All right? Get the number. I'm going to write up these solutions for you as soon as I can. I'll write up the solutions to this worksheet up through problem 7, and you can do it. All right? Have a good day, everybody.